From the rivers that carve through our cities to the valleys that separate mountains, natural obstacles have always posed challenges for mankind. How to cross these barriers? How to connect communities separated by geography? The answer lies in one of humanity's most impressive feats of engineering: bridges. Bridges are more than just structures. They are lifelines, symbols of progress, and testaments to human ingenuity. This essay explores the fascinating world of bridge building, delving into the different types of bridges that grace our landscapes. We'll uncover the secrets behind their stability, exploring how weight is distributed, and the materials that give these structures their remarkable strength. Join us on a journey into the world of engineering marvels that connect us all. The most basic type of bridge is the beam bridge. Think of it as a plank of wood laid across a stream, simple but effective. In large-scale beam bridges, the plank is typically made of concrete or steel beams, supported at each end by abutments. The weight of the bridge and anything passing over it, like cars or people, is transferred directly to these abutments. Beam bridges are best suited for short distances where the gap to be crossed is relatively small. You'll often see them as highway overpasses, pedestrian walkways, or even just small bridges in parks. While simple in design, beam bridges are essential components of our infrastructure, quietly and reliably connecting us every day. Truss bridges take a different approach to strength. Instead of relying on solid beams, they use a series of interconnected triangles to distribute weight. These triangles, called trusses, are incredibly strong because they convert forces pushing down on the bridge into tension and compression within the truss members. This clever design allows truss bridges to span greater distances than beam bridges. Historically, truss bridges were often made of iron and steel, materials that could withstand the high tension and compression forces. While less common in modern construction, truss bridges remain a testament to early engineering ingenuity, showcasing the power of simple geometry in construction. Perhaps the most aesthetically pleasing type of bridge is the arch bridge. Characterized by their elegant curved structure, arch bridges have been around for millennia. Think of the Roman aqueducts, still standing today, a testament to the enduring strength of the arch. The secret to their strength lies in how they transfer weight. The arch shape directs the weight of the bridge and traffic downwards, through the arch itself and into the ground via abutments. This compression force is what gives the arch bridge its remarkable stability. Modern arch bridges often use reinforced concrete, a material that's strong under compression, and can be molded into the graceful curves that make these bridges so iconic. Section 5. Suspension bridges, grace and grandeur. When it comes to covering vast distances, suspension bridges reign supreme. These structures are not just feats of engineering, they are symbols of human ingenuity and ambition. They connect places that would otherwise be separated by natural barriers, making travel and commerce more efficient and accessible. These engineering marvels evoke a sense of awe with their long, graceful decks, suspended from massive towers by a series of cables. The sight of a suspension bridge with its intricate web of cables and towering structures is both inspiring and humbling. It's a testament to what humans can achieve when they push the boundaries of what's possible. The Golden Gate Bridge in San Francisco is a prime example. Its orange towers and sweeping cables instantly recognizable around the world. This iconic structure not only serves as a vital transportation link, but also as a symbol of the city itself. Its striking color and elegant design have made it a favorite subject for photographers and artists alike. The key to a suspension bridge lies in its cables. These cables are the lifelines of the bridge, holding up the deck and ensuring its stability. They are meticulously designed and constructed to withstand immense forces, from the weight of the bridge itself to the dynamic loads of traffic and wind. These cables are anchored to massive concrete blocks at each end and draped over the towers. The anchorages are crucial, as they bear the entire load of the bridge. The towers, often made of steel or concrete, rise majestically from the ground, supporting the main cables that stretch across the span. Smaller vertical cables hang down from the main cables, connecting to the bridge deck below. These vertical cables distribute the weight of the deck evenly, ensuring that the load is transferred efficiently to the main cables, and then to the towers. The weight of the deck and any traffic is transferred to the towers through these cables, and then down to the anchorages. This ingenious design allows suspension bridges to span great distances without the need for numerous piers or supports, making them ideal for crossing wide rivers, bays, and other large bodies of water. The result is a structure that is both functional and breathtakingly beautiful, a true testament to human creativity and engineering prowess. Section 6. Cable-stayed bridges, a modern solution. Cable-stayed bridges share some similarities with suspension bridges but utilize a different cable arrangement. Instead of the cables being looped over towers, they are directly attached from the bridge deck to the towers themselves. This creates a striking visual difference, with the cables radiating out from the tower like a fan. This design provides good stability and is often preferred for medium to long spans. Cable-stayed bridges have become increasingly popular in recent decades and can be seen in cities around the world, adding a touch of modern elegance to the urban landscape. Section 7. Load distribution, the science of support. Regardless of the type, all bridges share a common goal: to safely transfer weight. This fundamental principle is what allows bridges to span vast distances and support the dynamic loads they encounter daily. From the smallest pedestrian bridge to the largest suspension bridge, the science of support is at the heart of their design. This is where the science of load distribution comes into play. Engineers must consider various factors such as the type of load, the materials used, and the environmental conditions. They use complex mathematical models and simulations to predict how a bridge will behave under different scenarios. When a car, train, or even just a person crosses a bridge, their weight isn't just sitting on one spot. Instead, it is spread out across the entire structure, ensuring that no single point bears too much stress. This distribution is what keeps the bridge stable and safe for use. It's distributed across the entire structure. This means that the forces are spread out, reducing the risk of any one part of the bridge becoming overloaded. This is especially important for long-span bridges, where the weight of the bridge itself can be substantial. This distribution of forces is crucial. Engineers must carefully design the supports and foundations to handle these forces. They use a variety of materials, each chosen for its specific properties, to ensure that the bridge can withstand the loads it will encounter. Engineers carefully calculate how weight will be channeled through the bridge's design. Whether it's through the arch of an arch bridge, which naturally directs forces down into the ground, the cables of a suspension bridge, which distribute the load through tension, or the trusses of a truss bridge, which use a framework of triangles to provide strength and stability. Understanding these forces, and how different materials react to them, is fundamental to building a bridge that can stand the test of time. Engineers must also consider factors such as wind, earthquakes, and temperature changes, all of which can affect a bridge's performance. By combining their knowledge of materials science, structural engineering, and environmental factors, they create bridges that are not only functional but also resilient and enduring. Section 8. Materials, building for strength and durability. In this section, we will explore the critical role that materials play in the construction of bridges, ensuring they are both strong and durable to withstand the test of time and the elements. The choice of materials plays a vital role in a bridge's strength and lifespan. Engineers must carefully select materials that can endure various stresses and environmental conditions. This selection process involves rigorous testing and analysis to ensure the materials meet the necessary standards for safety and performance. Two materials stand out: steel and concrete. These materials have been the backbone of bridge construction for decades due to their unique properties and versatility. Each material brings its own set of advantages and challenges, making them suitable for different types of bridge designs. Steel is known for its high tensile strength, its ability to resist being pulled apart. This property is crucial for bridges that experience significant tension forces, such as suspension bridges. The flexibility and strength of steel allow it to span long distances without compromising structural integrity. This makes it ideal for bridges that rely on tension, like suspension bridges. Suspension bridges, with their iconic cables and sweeping spans, rely heavily on steel to maintain their shape and support heavy loads. The use of steel in these structures ensures they can handle the dynamic forces exerted by traffic and environmental factors. Steel is also very good at handling compression, making it suitable for other bridge types as well. Its ability to withstand both tension and compression makes steel a versatile material in bridge construction, capable of adapting to various design requirements and load conditions. Concrete, on the other hand, excels at resisting compression but is weaker under tension. This makes it an excellent choice for components of the bridge that are primarily under compressive forces, such as piers and abutments. The durability and longevity of concrete make it a preferred material for these critical structural elements. This is why concrete is often used in combination with steel in bridges. By combining these two materials, engineers can create structures that leverage the strengths of both, resulting in bridges that are both strong and durable. The synergy between steel and concrete allows for innovative designs and efficient use of resources. The steel reinforcement helps the concrete withstand tensile forces, creating a composite material that leverages the strengths of both. This combination not only enhances the structural integrity of the bridge, but also extends its lifespan, ensuring it can safely support traffic and resist environmental stresses for many years to come. Section 9. Conclusion: Bridges to the future. From the simple beam bridge to the majestic suspension bridge, these structures stand as testaments to human ingenuity. They connect us, facilitate trade, and inspire awe. As we look to the future, bridge engineering continues to evolve. New materials, innovative designs, and advanced computer modeling are pushing the boundaries of what's possible, leading to stronger, more efficient, and even more elegant bridges. The next time you cross a bridge, take a moment to appreciate the marvel of engineering that lies beneath your feet. It's a testament to human innovation and our enduring desire to overcome obstacles and connect with one another.